Hi, my name is Maria. I am from Brazil and I am participating in the Asia Pacific Conference of Young Scientists as member of the Brazilian delegation. And my project's name is Analysis of the Origins and Dynamics of the South America Magnetic Anomaly as a component of the Earth magnetic field. And just to before starting talking about the research, I wanted to talk about my motivation to do this research project because like jumping straight to the definition of what is the South Atlantic magnetic anomaly, it is the region of lowest magnitude of the geomagnetic field. Main component that in Brazil we use B, but like across the world people tend to use F to identify this component. And it's basically the region that we have above South America currently that has the lowest magnetic field intensity of all the geomagnetic field. So my motivation to start to study this phenomena and mainly why and how it takes place inside the geomagnetic field, the Earth magnetic field, it was uh, it was presented to me like it was presented to me this phenomenon through a lecture in the Institute of National Space Research Institute of Brazil. That here it is, and it's basically the greatest research facility in the southern hemisphere of the Earth that studies space and has a space lab actually. So I was like participating, and one of the lecturers showed us this, and he still works with space climate and space weather, and I found very interesting. And as soon as I learned that there is not really an explanation, like a solid explanation for why summer happens, that is that stands for South Atlantic Magnetic Anomaly or South America Magnetic Anomaly. I decided that I wanted to give my contribution on it, and I have started doing this research project. So basically, the origins of Summa are commonly attributed to the offset of the geomagnetic dipole of approximately 11 degrees and 500 kilometers from the geometric center. But like, although this is a good picture of what causes it, it doesn't really tell us nothing about the cases, the causes in the actual physical process behind it. So like, how does the geomagnetic field being inclined in 11 degrees and being decentralized in 500 kilometers really causes a magnetic anomaly in the Earth? This is what we don't know actually. So I just put like some references here. So the true origins of Sama considered a fundamental problem in geomagnetism for the reasons that I just told you. And so this is like a good picture of what exactly is this 11-degree declination, and the 500 kilometers offset, the decentralization actually is best pictured as the cause of the anomaly, but not by the physical process behind it. So I decided I wanted to study that. So basically, this is part of my justificatory, like why is necessary to study this, but also because besides the anomaly existing and being like a nice thing to study, a necessary thing for us to dive into, it has also a lot of implications for space research and space technology, because being a region with less intense magnetic field allows particles and energetic particles and radiation particles to dive more deeper in this region than in every region of the Earth. So every space technology that comes into this region has like a bigger chance to suffer like some kind of damage on its electric circuits than in other regions of the Earth because of this anomaly. Another part of my justificatory consists in about like, so we have a lot of magnetic models currently. We have the International Geomagnetic Reference Field, and we have the World Magnetic Model that both tries to picture the geomagnetic field through harmonics and mathematical equations, but both of them are very imprecise when it comes to time. So they need current update so they can keep track of the changes that the magnetic field accumulates over time. So I have here a graph that shows the magnetic declination for the year of 2010 according the IGRF of for that year, and for 2019 actually, for that same component, and you can see how many degrees does that change accumulates in. So you can see that the IGRF was predicting a very similar field to the actual field in 2010, but not really 9 years later. We have some other inconsistencies in the, but not really on the geomagnetic field, not really on the geomagnetic models, but actually things of the geomagnetic field that we don't know exactly how and why they happen. Like here, I have a screenshot of the locations of the geomagnetic poles. So the geomagnetic poles are the blue ones, and you have the poles, actually, the magnetic poles and the geomagnetic poles. The difference is just that the geomagnetic poles, they cross inside the Earth, and the magnetic poles are just located on the surface of the Earth. And you can see that the magnetic poles change much more drastically than the geomagnetic ones. And you can see also that the northern magnetic pole changes more drastically than the south magnetic pole. And I have some other inconsistencies here that support my claim that we need more accurate magnetic models, and we need to understand magnetic field better. And that because South America Magnetic Anomaly is a component of the magnetic field, so through understanding the anomaly and through understanding the field, we can say more about it, and we can come up with better models to describe it. But I don't think I will have time to dive into these other inconsistencies, but they are very, very interesting. So I am basically saying that there is a rising necessity for more accurate and more precise magnetic models to describe the Earth magnetic field, and consequently explain the origins and the dynamics of some components of the magnetic field, such as the geomagnetic poles, such as the magnetic poles, such as the declination changing drastically from one year to the other. And one of these components is actually the magnetic anomaly that we have above my continent, which is South America continent. Yeah. My research objective consists in summarizing the limitations in the current models for the geomagnetic field through a bibliographic research, which I have started to do here. I don't have time, unfortunately, to talk about all the limitations, but they exist. I will analyze the applicability of alternative experimental models on the generation of a magnetic field in the same qualities as the Earth's, and on the generation of a magnetic anomaly. So I'm like studying which models I can use to describe the Earth magnetic field, because we cannot open the Earth inside and see how is it, and to study and describe it more properly. So it might be useful that we use some magnetic models that we can, change the variables inside to produce a magnetic field in these circumstances, so we can understand the magnetic field of the Earth. But we need to have some variables that are constant, some things that are constant in these magnetic alternatives, these models, and with the Earth. This is why I'm going to do. And I'm going to carry out experiments and statistical analysis to assess the generated anomalies. And I'm going to compare, okay, which are the things and variables and results and the aspects of the magnetic fields and of the magnetic anomalies that I will try to perform in the magnetic models that are similar to what we have on Earth. And what can we learn about Earth by learning what I have performed in the magnetic models. So this is basically what I am trying to do. So the methodology is basically studying what do we need our model to be like, how our model needs to be like if we have Earth magnetic field like this and this and that. So the Earth magnetic field is divided in various sources, but the only source that actually matters to us is the main one, because it makes up more than 95%. So it's basically, because it makes up more than 95% of the total geomagnetic field, it only that source can cause the South Atlantic Magnetic Anomaly. Yeah. And we have here some components, because I'm going to talk about the components, but basically the only thing that happens that matters for the South America Magnetic Anomaly is the F, because it is where it happens, where it takes place. So all the others we can kind of ignore for this reason. And here there are more inconsistencies, but I will not have time. But okay, so if we want to find models that fit, or so if you want to compare the Earth with some magnetic models, we need to know how the Earth is like, and the Earth has a very complex way to generate the magnetic field that we see on the surface. That is the main magnetic field. They generate the main magnetic field inside the outer core through a self-excited dynamo that is a bit complex to explain, but involve like the movement of the liquid parts of the earth. So they move and they generate a current, and it is self-excited in the sense that the field lines that we see on the surface and the field lines that we see inside the outer core, that we cannot see, we cannot measure the outer core field lines that are toroidal, basically like a donut. We cannot see them at surface, and we cannot see poloidal field lines inside the outer core, but they keep reinforcing each other. So it's basically like this. So we have toroidal here and poloidal out there. So whatever model that we come up with that we want to try to compare with Earth, it needs to have a poloidal field in the sense that we have a North Pole and a South Pole. So I'm going to switch for my article to say that the models that I studied and found more feasible to compare with the Earth was the bar magnet and the solenoid, because the bar magnet and the solenoid, they both produce poloidal magnetic fields. So this is basically the experiment that I set up to try to produce inside the bar magnet and inside the solenoid magnetic anomalies, which we can compare with the Earth's. So this is the bar magnet, and this is the experiment that I set up for the solenoid. A solenoid is basically like an electric magnet. So you have current flowing inside the wires. They are curved in the same direction, and you can produce a poloidal field like this. But you have an even stronger poloidal field if you put something metallic inside, in the sense that it's ferromagnetic, so we can increase the magnetic field that we measure, rather than if you just had like an air core without anything inside. So this was the experiment that I set up, and I decentralized this bar magnet in the same sense that the Earth is decentralized, but we cannot see what is the implications of the Earth being decentralized. Like I told you in the beginning, it doesn't tell us anything about the actual reasons behind the actual physical process behind it. So I am trying to figure out, kind of simulate them. And for the iron core, it's basically the same thing. So I will not change anything on the wires, but I will change where my iron core it is. So I change basically the location. So I am decentralized the iron core, so I can produce also a magnetic anomaly. And for this experiment, I had like a little bit more of control than I had for this one, because this one it is a bar magnet, so you can measure from various distances. But this one inside, you can see more of a control type, in the sense that if you measure from here to here, you have to have the same result. So if you put your detector here, which are the same distances from the point that you want to measure, you need to find the same value for the magnetic field that we are trying to measure. So basically the D segment, it has to be equal to the C segment, because they are at the same distance from the detector. And this allowed me to have a bigger control in my results. So moving on to the results, I'm basically trying to set up magnetic anomalies inside these magnetic models that I have already justified to be alike Earth, sufficient like the Earth, so we can compare, because they also produce poloidal fields like the ones we see at surface. So basically, the results that I got is that, let me switch to the graphs, it is a little bit easier. So for this one, I used Gauss. I didn't use Tesla. I think that the app that I was using my cell phone, it only it only measured for Gauss. It didn't measure for Teslas, which is the measure that I use, the quantity that I use for the next experiment. But it's the same thing. So I basically compared how much we have of a difference at Earth. So how much is the strongest and less intense region of field inside the Earth, how distant, how different they are, through basically solving for the difference percentage. So you basically resolve for the different percentage. And for the Earth, we have exactly, let me see, I don't really remember, but yeah, the Earth is 86.6%. So the less intense region, which is the summa, the magnetic anomaly, is 86.6 different from the more intense region. And for each experiment, I set up them in order to discover this, so I can simulate magnetic anomalies. And for this one, I got 74.55% from the more intense region to the less intense region. And for the solenoid, I got a various values of percentage difference, but the greater percentage difference that I got was 41.38%, which was, if you compare the segments here with the scheme that I have here, it is the equivalent of comparing the F segment with the I segment. So it's basically the greatest distance that you can put your iron core from one side to the other side. So it's basically if you measure F and you measure I, which is this one. So you measure measure here, which will be the strongest field because it's the closest region that we can have from the detector, and you measure I because it's the furthest region that we can have from the detector, from 0.5. So I got 76%, yeah, 74% for the bar magnet, and 41.38% at the most for the solenoid. And this basically means that both experiments, they reproduce fields that are like the Earth in the sense that they are also colloidal, and we can use the mechanism that some researchers pointed out as the cause for SAMA, which is the offset of the magnetic field of the Earth, being centered 11 degrees tilted and 500 kilometers decentralized from the actual center. And basically, we can say that a valid conclusion is that a magnetic anomaly could be generated at Earth through a decentralized outer core. So because we generated magnetic anomalies inside a field that is basically like the Earth because it's colloidal, in both experiments, the bar magnet and the solenoid, we can say that a valid process is through which SAMA takes place at Earth is through a decentralized outer core, just like we had on the Earth. So thank you for listening, and bye.